Okay, welcome everybody. And we have a guest speaker today, Christina Reissel from MIT. And she will be talking about machine learning for real-time analysis of gravitational wave data, which is a very exciting topic because gravitational waves are the new way to look at the universe and study cosmology and our universe in a very different way. So it's exciting.
In a few weeks, we'll have neutrinos.
Oh, there you go.
Yeah.
That will be even better, yes. So, Herman will talk about. All right, Christina, thank you.
Yes, thanks. Yeah, today I will present, as you already mentioned, machine learning for real-time analysis for gravitational wave data. And I will basically present the efforts of the so-called ML4GW team. It's a collaboration between MIT, Minnesota guys, and also some other folks from Taiwan. So yeah, and we basically try to build up a full pipeline for the analysis of gravitational wave events. Just to start with a very broad picture, as it was already said, like multi-messenger astronomy is an essential feature to gain information about the structure of the universe and actually astrophysical objects. And I hope I do not have to convince here anyone that it's of course necessary that we use every probe that we can to gain the most information that we have. So what we can do is electromagnetic waves. So this is actually this nice overlay picture of infrared and gamma ray measurements. Then we can use neutrinos, as it was already mentioned. And then since the discovery of gravitational waves in 2016, with this event from 2015, actually, we now have a new probe to actually gain these insights in the structures of the universe. Particularly important is that we if we want to use, of course, all of these probes on some event, however it looks like, we have to share the information that there was something interesting happening and also the properties of what we have found. So it's essential that we can do this data analysis as quickly as possible because, for example, electromagnetic signals usually occur very shortly after we have measured a gravitational wave event. So like this exchange of information is very important. When you speak about gravitational waves, we have several detectors around the world. We have the LIGO scientific collaboration that has two detectors here in the US, one in the state of Washington, Hanford, and the other one in Louisiana, Livingston. Then we have Virgo detector in Italy and the Kagura one in Japan. And why I put the pictures here, it's not only because it's nice on the slide, it's also to demonstrate how actually different the environments are where these detectors are in. So we actually see here that Hanford is kind of a desert, Livingston we have the forest, Virgo in Italy is actually in a very populated area, and then Kagura is underground. So when we develop algorithms, what we usually try to do is that they can actually manage this very different conditions and optimally be deployed on different detectors. So in terms of sensitivity, LIGO is the most sensitive one. So we measure this usually in megaparseconds, which is like the reach of the detectors that we have. And Virgo is a factor of 3 worse compared to LIGO. And then there's another factor of about 10 to Kagura. So basically, if we do measurements, they're mostly driven by LIGO and Virgo measurements at the moment. Just a quick word about the experimental setup. I'm not a very detector person, but just to tell you a bit how this data is actually measured. So the basic principle is kind of easy. It's a Michelson interferometer. But what is kind of fascinating is what kind of adaptations we have to make to actually reach the sensitivities that we need to measure gravitational waves. So basically, you can see here the 2 arms of the detector. And then we basically have to increase here the effective arm length that is built to be actually 4 kilometers to about 1,200 kilometers. And this is done by these Fabry-Perot cavities where the laser beam is actually basically bumping back and forth 300 times that we reach this effective distance. We also basically have here laser that can provide 40. To sharpen the inference pattern, we need about 750 kilowatts. So also there are like specific power recycling mirrors so that we actually can reach this power. There are a lot of other improvements, a lot of tremendous work regarding like also signal recycling mirrors and particularly the seismic isolation system. So here these so-called test masses, the mirrors, they have to be very decoupled from actually ground motion, which is a problem in itself. So yeah, as I said, like this whole detector, it's a kind of basic principle, but it's actually very advanced when we come to all of these details. So as we're speaking about data analysis, what does our data look like? So in both detectors, we measure time series data. So we basically just have a time series and we measure if there's a signal like in this inference pattern. And actually, this is a time from the Hanford detector data. And I can tell you that there was a gravitational wave in that like this, you can of course not see. But there are specific data pre-processing steps that we always take that we also do before we actually plug any like machine learning method or so on top of this that help us to analyze and understand this data better. So since we're speaking about time series data, one thing that you, of course, can always do is you can go to frequency space. This is what we do with the fast Fourier transform. And for doing so, depending, of course, on also for which frequency we want to be sensitive to, we choose a window size. We can then do the Fourier transform, and then we can also go back. This is why, like, this is again the time series after this two transforms, why here it's labeled windowed. Because basically you're not sensitive then to all frequencies anymore, depending on your window size. Then a very essential step is the so-called whitening. So what we do here is we get are basically in Fourier space here, and then we divide by the background. So we basically force the covariance matrix to be unity. So that helps us to decouple the different frequencies, and basically we would expect then each frequency to contribute at the same amount. And now you're asking why now we have like this kind of wide spectrum that looks actually worse than before, because you basically only see noise. The idea is when there's a signal, this will actually now pop up over this background. And if we now do the bandpass for a certain frequency range, we can actually now see that there is this gravitational wave signal that you can even by eye now clearly see that is distinguished from like this background.
So talking about background, so what are the contributions to your background?
This is, I will actually speak about this in terms of the denoising just in a minute, but this background is very complex. I will just like to speak a bit more about this when we come to this part. Yeah, so we basically now have only spoken about one time series. In reality, we have actually two from the two Dieget detectors that we usually treat basically at the same time. And we also have Virgo usually also running. And why we have multiple time series is actually, I mean, there are a lot of good reasons for doing that. The first one is we want to measure the localization in the sky where an event is coming from. And for this, we have to do triangulation. And for this, we need multiple measurements. The second part is also noise, because as we will also discuss in a minute, this noise is very like, I mean, it's very different between the detectors, and most of the noise sources will not be coupled between them because they're so far apart. There are actually some studies that like some things like thunderstorms in the US might affect both detectors at the same time because of like the power grid. But these effects so far were studied and were like found to be very minor. So we can kind of safely assume that the noise is actually decoupled. And so the only thing that basically will lead to a coherence, a correlation between the two time series will be a real astrophysical signal. Then, of course, we have increased sensitivity because if we measure several times, it's like just a general thing. And we can additionally use the timing. So like gravitational waves will travel several milliseconds between the detectors to even gain further understanding where this event is coming from and all of these things. How we usually identify, let's say, classically, and signal in this time series is that we can, from very good models, generate templates, and then we do a matched filtering algorithm. So we basically slide what we would expect to be a signal over the time series, and then we basically, easily speaking, say we see where it fits our template. And then we say, this is an astrophysical event. And because we know how this template was generated, we can even say something about the properties of this event. Just to mention it here quickly, often in like the literature, you will also find these kinds of spectrograms. They are basically showing again the frequency information versus the time For our algorithms, the one that I present today, we do not make use of this information. We use directly the time series as an input, but just basically these kind of visualizations are very handy usually because it's a kind of like compression. You can also use this, and particularly if we want to distinguish very short duration noise, so noise that is actually very similar in the length to our astrophysical signals, these kind of frequency representation can show us very nicely like the discrimination, because the signal is usually very localized here in the frequency space, while the background will be having a lot of different frequency contributions. So just when you see something like this is also a very common way to show it, but I will not speak in detail about this because this is not what we're currently using as an input.
Could the match filtering algorithm be run in frequency space? It's just convolution, right?
Yeah,
Transform that.
I'm pretty sure that this information is taken also somewhere into account. I think the classical one not, but also I'm not completely aware of like where it's run, like the classical one, like what is exactly using the inputs. There are also several versions of like it for several signals and so on. Yeah, I know that, for example, in particular for discriminating transient noises versus the signal, there are also algorithms that, for example, train directly on the spectrograms as like images, basically. So when we just speak about the total analysis pipeline, what do we need? So we have like this time series as an input, usually, as I said, from Livingston and Hanford, but of course it can be extended for the other detectors as well. The first step would be that we want to do a denoising. And there we always distinguish between the so-called locally stationary noise and the transient noises. So locally stationary noise is something that persists over seconds, hours, days, but can change. So a typical example would be actually an AC unit in Hanford that is turned on and off by people, or a train that is coming, or something like this. So it's actually not on the time scale of an actually astrophysical event that is usually seconds, but really over longer periods of time. Then transient noises are usually what we also call glitches. It's a short duration noise that is very similar to actually the signal, but is like very short in duration, and you can usually see it also in the spectrogram area. It has like very different frequency contributions. When we have denoised the data, the next step would be a detection. There we basically run detections for known signals, which is something like binary black hole mergers. But we also would like to look for signals that we do not know a priori, or we can just not model. So we do not have very well or very difficult models for it. And then, of course, if we detect something that is interesting, we would like to know the characteristic of this event. So we would like to know, for example, what are the masses, is the position of the event, the polarization, like, of course, all of kind of information that we have. So what does it mean in terms of statistics? I just tried to make it up here a bit. So like denoising is just a regression analysis, basically. So here our target would be the combined noise budget. The good thing is that in all of these detectors, we have so-called witness channels that monitor the environmental condition at all times. So we can actually use this as an input for a regression to actually determine the combined noise budget. This is highly nonlinear because these couplings are like far from being simple. So of course here, kind of a natural thing would be to come on with machine learning to actually learn this highly nonlinear couplings and to actually, predict then this combined noise better. In terms of detection, this is, a simple hypothesis testing. So our alternative, one hypothesis is basically being background. The other one would be signal. There, perhaps in terms of the known signals, an interesting point is that we usually operate this algorithm as very low type 1 errors. So we want our false alarm rates to be very small because we would not like to trigger all of the other like telescopes, observatories in the world just because there was like, we are not really even sure if it was something interesting. So usually what we are interested in is like triggers that are very low type 1 error. In terms of unknown signals, of course, this is always a kind of ill-defined problem because we do not have an alternative hypothesis. So anomaly detection is always a kind of like more complex thing here. But the good thing is that we actually have classes of models that usually we believe can describe somehow what an anomaly would at least somehow look like. So we will come. Yeah.
I understand how you would set up this hypothesis testing with the type 1 error when you have one time series, but now you're looking for simultaneity or even some sort of a small measurable shift between multiple detectors, multiple time series. Is there are there any changes that you got to do to your process to set the type 1 error, type 2 errors?
No, so like what we do is when we just come to this in a minute in terms of machine learning, we basically just have as an input the two time series. And then the algorithm itself will be trained on this and it will learn features like, for example, the correlation. And then we anyway project it down to a score. And this we use then as a test statistic for that actually hypothesis testing.
Okay.
So it's actually test is done on a scalar score. Yeah.
Okay. Right. Thank you.
Yeah.
Sorry, may I have a follow-up question?
Yeah, sure.
So during your testing procedure, are you simultaneously learning the background models for statistical gravitational waves? I know that statistical gravitational waves are very complicated, as maybe someone pointed out. So are you learning it simultaneously for your machine learning algorithm?
So for like this detection that we're targeting here, not because the stochastic gravitational wave background is just like signals that are so long in duration that they are not really affecting this here. Just also by the kernel size that we use in these trainings. I will also come to this in a moment. For actually the denoising part, this is an interesting problem that we also have thought about. So far, what we believe is that because we use here these witness channels, which are not affected by the stochastic gravitational wave signals, we are kind of sure that this will not like kind of accidentally filter out like stochastic signals, just because these witness channels, how they are set up, are so-called safe. So we can make sure that no signal is actually backpropagated to this witness channels. And we actually have run also for example, this denoising, and we saw an improvement for specifically the stochastic gravitational wave background searches, because especially if we clean away this longer duration noise, this is very helpful with this like long duration searches, as you like just would expect. Yeah.
Okay. Yeah. Thank
you. Yeah. So this is basically the detection part, and then of course, if we have detected any form of event, we would like to know all of the information that we have, which is a parameter estimation. So we have some parameters here, theta. We have a likelihood that is usually complex, highly dimensional, all of these issues that we often have in physics. And so the classical method here is an MCMC. There, the issue is, of course, what is always the problem. It's very time consuming, especially if you want to sample higher dimensional spaces. So this usually here takes about like hours. And this is, of course, for low latency deployment, not very optimal. So this is also why we have been working on that. And now, why do we want to actually be quick? I mentioned it already several times. We want to send an alert with as much information as possible, as quickly as we can, to basically all other observatories. So we need low latency, high throughput, and excellent sensitivity. Low latency here, we target usually something about seconds. High throughput, we want to run it all of the time. And excellent sensitivity, of course, because we do not want to trigger all of the other experiments, just if like there's some like weird looking noise event or something like this. I know that now here in the room, it's not so easy to see, but I really like this kind of graphic here by the A3D NSF Institute, showing the latency requirement in seconds versus the streaming rate. And like this blob is the yearly budget. And this pink one here is LIGO. And you can see that we here in the latency requirement of 0.1 to 1 second with streaming rates of 10 to the power 7, 8 bytes per second. And this is, for example, in more extreme environments than Netflix. But as you can compare it, for example, to this Large Hadron Collider blob that is here, the level 1 trigger from the at CERN is still like not as extreme environments. So we can actually deploy all of these pipeline on GPUs still. So like we do not have to go to FPGAs or ASICs or something like this. Yeah.
So what is Netflix?
Netflix is the gray one on the.
Yeah, but
Right.
this is like, it's an experiment or is it just?
No, I think it's basically really the data that like they use like and analyze for the Netflix. Yeah, yeah. Yeah. And yeah, like this one is Google. So this is also the Google Cloud.
Oh,
This
really?
is also like something I always find very impressive, like in what kind of extreme environments we are also like with all of these physics experiments. Yeah, and because we do machine learning, we of course also like to give like fancy name to things. And so we have developed basically an algorithm for all of these tasks. And with these names being shown here, so for the denoising part, declean, for detection, A-frame and guac, and then for the source parameters, amplify. And then now we'll go like one by one to all of them. So as I already mentioned, LIGO noise, and also the question, it's very complex. So we see the frequency versus the amplitude spectral density here. And it's very hard to navigate through, but I just want to highlight here some things. So we have a broadband noise that is basically given here, that's shifted up. Then we have the spectral lines. Then, as I already explained, we have locally stationary noise where this is glitches. Because this plot is made over a longer time, basically everything that we see here is this locally stationary noise. And this is also what we target to clean with deep clean specifically, because we can train on longer segments of data. And we can use this information then to actually clean. Where is this noise coming from? So we have the AC power grid. So these are typically the spectral lines that actually is 60 hertz, where is it? Yeah, here. And then all of the harmonics as well, 120, 180 hertz. We have mechanical resonances and the detector control systems. And actually what we also have, but this was kind of like weird to me first, was that there actually is noise that we inject with a little motor by moving the mirrors. And this is for calibration purposes. And we know where this line is going to end up. But also sometimes these lines, I mean, we need to filter them somehow out again. Like we know, of course, where they are, which is not like why they are like super hard to clean. But this is also something. All of this is monitored by around 200,000 auxiliary channels. So these are like voltmeters, seismometers, basically all of the kind of detectors that you can build for monitoring these environmental conditions. Out of these 200,000 auxiliary channels, we have around 1,000 per detector that we consider safe. So safe means basically they're well understood. They have sampled at a frequency that we can here easily make use of. And we are sure that there's no signal that is like coupling back to these channels. So they are considered signal free. All of this is tested in actually injection tests. So people are really going there, like applying forces, and so that we can really make sure that this is like how we assume it is. And just as a rough rule of thumb, what we can say is that low frequency noise is mostly angular and controls noise. And above higher frequencies, we have quantum noise here. With deep clean, we focus mostly on the low frequency parts because, yeah, we have there this noise, and also the noise contribution here is much bigger and also more limiting towards like the signals that are usually here around like the below 100 hertz.
So when you put the signal on that plot, where do you expect the signals to be and how high?
Depends, of course, also on the masses and so on. But usually, I think the first event that we have just shown was around like 30 to 50 hertz. So it's like really here, like, I mean, it depends also like at which stage we can detect the signal. So like if we really only like are sensitive to like the very large, the very last stage where they basically are shortly before collapse, for example, in a merger, or if we are sensitive to more of this spiral phase, this also changes, of course, the frequency.
But it's all around this 30.
Yeah, it's usually around like this. We say like up to 200 hertz is actually where the signals are. Yeah. Yeah, what do we do then for denoising? So the idea is here that we take a subset, like depending on the frequency band that we are interested in. Usually we target frequency bands between 5 and 10 hertz. And we take then the relevant channels in this band, 5 to 10, 20 into account. We train a convolutional neural network on them, which has like this encoder decoder structure. So we basically project everything to a Latin space, and then we decode from there. And by this, we learn the predicted noise. So basically the combined noise that we would expect from these channels. And then we take the signal, this trained channel, and we subtract this predicted noise. And we can do the power spectral density ratio between our original one and the clean one. And we use this as a loss function. So basically something that we would like to minimize. And then by this, we update here the weights. So of course, all of this is kind of like working well, as long as we know what kind of witness channels to use per frequency range, which is actually not an easy problem. And this was something that we have just currently been working on, because what we need for this is a coherence monitor. So we have to basically monitor the conditions in the detector every day, because these contributions also change. Okay, here on the projector, it's a bit hard to see, but basically we have set up this coherence here, where we have for each frequency between 0 and 200, we plot here the witness channel with the highest witness channel is just basically a channel that monitors a certain environmental condition, for example, a voltmeter, or
So it's not the signal that you get from the phase and from the interference of the lasers, but something like temperature.
Yeah,
you know,
exactly.
just something that might be related to finding any signals, but it's not directly related to the actual signal that you're getting.
Yeah, exactly. Yeah.
Okay. We, in the spacecraft world, we call that housekeeping.
Exactly. It's basically kind of like complex housekeeping, yes.
Yeah.
And so basically the documentation looks like something like this then. So we kind of like are plotting here for every channel the coherence, and then by looking just at like this, we can see that there are frequency ranges where we have a lot of these information from the witness channel, so they have a high coherence, and then we can use these channels basically to be plugged into deep clean and actually denoise the data. And the color here is just like the different groups. So SAS would be suspension, so it would actually be like related to some seismic motion in the detector. So the whole pipeline looks then like this. We ran the coherence monitor currently, actually starting from October on. It's run 4 times a day, so every 8 hours. We monitor our conditions. Then from this, we require for certain frequency bands. We pick a number of witness channels that have high coherence. Then we plug them in deep clean. This training is completely automated. Also in the way that, for example, the learning rate, so basically how much it's learned from the channels, is updated automatically. Then we apply this cleaning that we get on independent data and see something like this. So this is the amplitude spectral density. And just to show you a bit more in detail, like the results that we get from this. So this is again the spectrum. This is from Hanford. We have here identified 6 suitable cleaning bands. I just highlight here the one that is at around the first harmonic at 120 hertz. So you see here this line that we know it's relatively well understood. It's the harmonic from the power line, but then there's a lot of like nonlinear contribution around it. And then when the blue one is basically after we have cleaned, after we applied the deep cleaning algorithm, and you can see it's basically flat. We have removed everything around this. And when we see it as a ratio of the clean to original, we have removed around 50% of the contribution in this frequency range. So it's actually working well, very well. And we can do so like for all of the other bands as well. One thing that kind of was also interesting to me as like a physicist, of course, we always question ourselves, like how much is actually learned from this, how much physics information. And you can see here, these are like magnetometers. And we found in the coherence monitor that 11.9 hertz, these two showed actually high coherence. And so when we plug them into deep clean, we are actually able to clean here away this little peak, because this is information that is used from these channels. If we actually drop them from the list of channels, so if we let not deep clean have a look at these, you can see that this peak is coming back. So it's really like we can relate like the channel, the information from the channel directly to the cleaning performance. And then something just that we wanted to do is like, instead of just showing this ratio, we also computed the so-called in-spiral range. This is basically a standard measure in gravitational wave astronomy that tells us how much of a reach we have in the universe with the detector. assuming that we have a binary neutron star in spiral event, where we have both neutron stars have 1.4 solar masses and a signal to noise ratio of 8. And we saw that for the signal range, we have an improvement of 1.4%. And then overall in the sensitive volume, if you do the cubic, we have around like 4%, which just like basically applying 6 times a cleaning algorithm is kind of impressive that we could like, I mean, by almost 4% of the volume, we are like more sensitive to. Yeah, this brings me then, if there are no further questions, to actually the detection part, which is like, we'll start with A-frame. So A-frame is looking for binary black hole mergers mostly. So this is a signal that we understand very well. And here the idea is that we have this time series here showing now a signal. And then we have a window that is actually 1.5 seconds. We move it over the time series, and then we get a scalar neural network output for each of these windows. They're actually overlapping. So we have a sampling rate of 4 Hertz. And then we take the maximum integrated value over 8 seconds as a test statistic to then do this hypothesis testing if it was background or signal. Yeah, just some like technical details here. So because I think in the context of A-frame, this is kind of impressive also to me. So the training takes 44 hours on a single GPU. The evaluation of this so-called O3, which was like several months of data taken out of both detectors, was 30 hours on 8 GPUs. And of course, I mean, this is all offline purpose, but the idea would be to really deploy it online, so run it in real time. And what we see is that we have here a medium latency of 3.9 seconds for this, which is more than 8 seconds actually faster than similar pipeline that I operated at the moment. Of course, we don't only want to be fast, we also want to have a good performance in terms of the sensitive volume we are sensitive to. So this plot here shows like the false alarm rate versus the sensitive volume. And this is several mass bins. So like this is for binary black hole mergers of like higher masses, so 35-fold to up to 10 and 20. And in general, as a rule of thumb, like the higher the masses, the louder the event is, the easier it is to detect. And we can see that in this higher mass bins, we actually we have the highest sensitive volume. And as you can also see in the x-axis scaling, that the false alarm rates that we present here go down as to 10 to the -2 years. So actually, these plots require analysis of 100 years of background data and 1.35 million of signal injections. So there's a lot of like technical things behind it just to like get these plots and make this algorithm run at scale. And then in terms of detection, we also have QUOC. QUOC is this anomaly detection algorithm that we run if we do not know basically what the signal looks like or it's poorly modeled. So the classical example with this kind of signals is core collapse supernovae. Usually it's quoted as one of those. And here our idea is that we use an autoencoder metric as a measure. So we have again here this setup of an encoding and decoding neural network. And the idea is that we train it on a certain class of events. And then we take the mean absolute error as in basically comparing the input and output. And if this network is trained very well, we would expect this mean absolute error to be very small. So basically, if it's trained on background, we would expect it can compress and decompress these events well. We have a good reconstruction. We have a small mean absolute error. When it sees something that is not trained on, we would expect this compression decompression to fail. We would expect a large mean absolute error, and then we can label this event as an anomaly. The problem with this one-dimensional setup as here is that we can say, okay, this is not part of our training set, but it's very hard to actually discriminate whether it does allow some form of noise, or is it actually true astrophysical anomalous event. So the idea behind this is then to not only use one autoencoder that is trained on one class, but actually use several of them that you train on several like backgrounds, several known signals. So for example, here, this is showing binary black hole mergers, which is the signal that we just spoke about for A-frame. It's the background. And then we have the so-called sign Gaussian, which is kind of a class of models that we believe can somehow give us an indication how an anomalous event would look like. And then we basically built this multi-dimensional spaces out of this. And then here by the colors, you can see that we then can determine certain hyperplanes in this space that we can use for selecting actually backgrounds where there's like different forms of backgrounds and signals. And then in real life, what it actually looks like, we have 5 of these autoencoders being trained on binary black hole mergers on 2 types of or 2 frequencies of the sign Gaussians. Then we have the autoencoder for the background, and then for the specific form of short duration noise, also the glitches, the autoencoder from the glitches. All of them take into as an input the 2 time series of Hanford and Livingston, map them down to a common Latin space, and then decompress from there. We additionally have a frequency domain correlator because, as I said, we would expect for real events to have a correlation there. All of this is then fed to another network that has pre-trained coefficients to actually, again, receive a scalar final metric. And you can see here, it's actually where we injected an anomalous event at this spot. And you can see that this matrix is nicely telling us that here's something happening.
So
Yeah.
in this way, do you also detect the binary black hole matrix, or it's coming as a background?
So here we could in principle because we have this autoencoder in, but the thing is that usually for this anomalous searches, there are usually less sensitivity than actually targeted supervised ones, because there we can use all of this information that we have about it. And here it's basically the idea is to have it not targeted too much for one signal, but really to be sensitive to a huge range of things. So yeah.
But what happens if you have that signal and
the binary black hole? So basically, if we have a binary black hole mergers here, this autoencoder would have a very low loss because it was trained on these events. So we could basically see that this is kind of giving us a lower construction loss, the other one a high one. And then we could basically, this was trained in a way to actually focus more on this anomalous events. So in this final metric, it would not be showing up, but we can also take the metrics of all 5 of them, and then we would see it in the metric of the binary black hole mergers that there was.
So you won't miss that.
Yeah, no. Yes, and this then,
So could you go back to your last slide? So if you had only 4 of these autoencoders, not all 5, you know how your results would change?
It depends a bit, because mostly what we know is that it's very hard to discriminate from the signals are these kind of glitches. So there are actually a lot of other kind of things that we have to take into account, specifically also this frequency domain correlation actually to suppress this. So when you I don't know the exact numbers, but I believe if you would leave this out, you would get a lot of events suddenly that are picked up, because just glitches happen a lot of the time and they're very hard to distinguish. Then we know that this longer duration background for this shorter signal, I guess it does not have such a big of an impact. And this 2 here, the sign Gaussians, is more for biasing basically in the space where we would expect anomalous signal. So basically this is kind of more an idea to build our space in such a way that we know where we would find, or that we have an idea where we would find the anomalous signals. So, and of course, binary black hole mergers, if you would leave this out, of course, you would also have basically have an anomalous score on each of these events, I'm pretty sure. Yeah.
So one question, how are those trained? I guess they trained using supervised learning. And the question is, where do you get the data from? Is it simulated material, or it's...
So what we always do is we take basically the so-called run data from whatever run we're interested in, and then we inject on the fly signals. So for A-frame, for example, this is really done on the GPU because we have to do so many injections. So we take basically the real background and then we just inject. And there are also models for glitches, for example. But here, I'm pretty sure that this is also all taken from data. Like this is really like labeled as a glitch from this time and then so on. Yeah. This is actually also perhaps just to mention from a like data science perspective, I find it kind of interesting because this is an advantage of these time series data, because what we do is we have basically infinite amount of background, because we can take the streams of both events, and then what we additionally, when we train in both, what we do is we take this background and we just move it against each other. And by this, we basically have a new data set that also is background, but it's just moved against each other. So we can basically generate an infinite amount of backgrounds to train on, which is very helpful for these kind of applications, which, for example, in particle physics is actually a way different problem. So this is somehow like a nice thing about these kinds of data that we're working with. Yeah, this brings me to the last algorithm, Amplify, which is targeting parameter estimation. So one, I mean, there are, of course, two motivations why to work on this. The first one is MCMC being very slow, not used for low latency. But then the problem is what we now usually in real life do more often is that when we do this matched filtering, we actually can say which of the template fits well to our data. And by having this data about the template, we can actually then already derive some of the parameters, or like in a relatively simple way. The problem is if we now apply A-frame that is much quicker, we just have this score. We do not have this prior knowledge about what parameters actually come into account. So we actually need a new low latency method to actually provide these parameters. And yeah, just to summarize here again, so we have like this parameters, there are actually 8 that we estimate with Amplify. We have the likelihood. What we actually measure in the detector is the signal that is somehow transformed plus the noise. And we can simulate this basically, or we know from simulations, the true underlying parameters and the data. What we do here is a 2-step approach that I find actually kind of interesting because it's also picking up a lot of these like new machine learning ideas. We do a pre-training and embedding that is using the same architecture as we also have for A-frame. So it's a huge convolution neural network. We project then the time series data down to 24-dimensional space. And all of this is done self-supervised. I will speak about this just in a moment a bit more. And then on this lower dimensional space, we train then a posterior approximator that is a normalizing flow, basically just flexible invertible parameterized transforms that then actually do the parameter estimation. Yeah, as I already said, what I find very interesting here is particularly the symmetry embedding. So this is something like, or this kind of self-supervised trainings we know from like large language models that are very powerful, because what we want to do is that we want to let the network figure out itself which kind of like properties or information to use to actually do the task. And what we are using here is the so-called Wick-Wright class, which is variance, invariance, covariance regression. But just to explain it now a bit more in detail, what we actually do is we provide the network by so-called 2 views of the data. So we have here, okay, this is not coming up so well here on the projector, but we have blue and red, which would be the 2 time series of Hanford and Livingston data, just overlaid. And then we have here, like basically it's a signal that is like injected so that basically the time of approach for the detector would be this line that you can see here. Yeah. And then we can basically provide this machine learning algorithm with another view of the data where we actually inject the signal at a different time. So we say we can shift the signal injections by 1 second. And we know that our physics doesn't change when the exact approach time of the signal is. I mean, it's a binary black hole merge, and it doesn't matter if it arrives now or in 1 second. So we basically force by this loss the network so that in the latent space, these 2 downwards projections will basically be equal. So this is what we are doing with the mean square error. So we basically tell the network, these should not be different. Please push them in the latent space to the same point. And by this, we can marginalize dependencies. So like here, we basically marginalize time shifts because we know that this is not important. But we can also do, for example, in particle physics, you can do like 1 normal view, 1 rotation, and then by this, you can basically make your networks rotation invariant. Or like the embeddings rotation invariant. Then the second part is basically that we enforce a certain variance in the embeddings. So like here you can see that basically the variance of the x's of the basically not transformed view and the xy slashes are like basically forced to be above a certain parameter epsilon. This is just to make sure that this whole thing doesn't collapse, so that not all of these embeddings end up in the same point, because this is also what could happen from here. I mean, there's no like kind of stabilizer for that. So this is basically what this term is doing. And then here, this is forcing the off-diagonal elements in the covariance matrix to basically be zero. So we decorrelate the embeddings. And this is to also prevent this information collapse. So we would not like to have embeddings where each of the dimensions are just shifted up and downwards all at the same. So we want really to have the maximum information stored in these embeddings. And this, like, just in terms of parameters, so we can say like the whole amplify network has 6 million trainable parameters, out of which 3, or roughly 3, are the first part, the embedding part, and roughly another 3 are then in the actually posterior approximation.
Can you say one more thing about what the C means here? I know you said decollage, but what is the function look like?
So this is just like the off-diagonal terms of the
These are actually just the off-diagonal terms themselves.
Yes, I think so, yeah.
But why that's positive?
Sorry? So we like, I mean, this whole thing is minimized. So like we push them towards 0, basically.
Yeah, but these C themselves are always positive.
It's the norm correlation. It's always
Yeah.
positive.
Yeah.
It's all correlated.
It's not. It's by construction.
Oh, okay.
Yeah, and then we come to the results. So this plot here shows like for in the 8 different colors, the 8 parameters that we estimate. This is the confidence interval, basically scan, and this is a fraction of events in this. And this is basically just to show that we do not have a bias here in the estimation, and also that our uncertainty covers it very well. Then, I mean, I know that we show here 8 parameters, but the most important one out of this, I would say at this point, is of course the sky localization, because it's a very important input for the alerts. And here we actually compare the amplify versus Baystar. Baystar is basically this algorithm that computes the localization based on this information that we have from the template matching. And you can see here that this is actually real events from all 3. And that, okay, here it's also hard to read. The 90% area, like for amplify, in this case is actually still larger than for Baystar. But then when we go to louder events again, higher math events, we see that amplify is actually comparable or slightly better than Baystar. So of course, there's still some work to do to really reach everywhere the same sensitivity. But I mean, yeah, we can see that we have already here very nice results with this algorithm. Then just to give basically one quick slide on the whole deployment. This whole deployment is not also like kind of advanced. So because what we want to do here is that we want to train these models, then we have to store them somewhere, and we want to regularly update them. So for example, deep gradient is an algorithm that we know needs like perhaps more regular updates, where this amplify has been shown to be relatively stable. But we of course like need to manage like the versions of the models that we have trained, and then which ones we actually send for inference. So here we have something as inference as a service, where we have a server where all of these models are stored, and then they're basically sent to like other hardware, like for example, also, I mean, GPUs, which are the most useful here. And then, of course, from this, we hopefully can also learn them, and we can like take this into account in training more advanced models. We store them again, we can deploy them. So all of this is also very nicely here summarized in this paper by Alec Ghani et al. From Nature Astronomy. So when you're interested in more like this kind of technical stuff about how we actually do this in the end, I recommend checking out that paper. And this already then brings me to the summary and outlook. So I hope I could convince you today that we are like working towards this complete AI pipeline that include data denoising, event detection, and parameter estimation. Our emphasis here is real-time processing, because we would like to improve multi-messenger prospects. for this gravitational wave observatories, we focus on the low latency, so order of seconds, minimal computational footprint, maximum throughput. In terms of future work, so we are currently working on the low latency deployment on all of these algorithms that I have presented today. They're kind of in different stages. So A-Frame and Amplify are in what we call the internal review process already. So they're basically ready for the review. Walk is almost there. It's just a matter of days or like weeks. So I think like the plan was to start this review at December. But Deep Clean, there's still some work to do. And then, of course, like we also in parallel start like looking into improvements that we can do, for example, using more advanced machine learning tools. As you have seen, basically the challenge for all of these algorithms is that we want to apply them to time series data. So of course, we have learned a lot like in the different applications, and we were thinking about using perhaps more unified models for all of these applications. Of course, there's always like also these ideas about using more modern tools in the sense of like speaking about transformer networks, etc. And in general, what I also would like to highlight here is that in principle, all of these tools are not very like tilted to gravitational wave astronomy. It's just can also be seen as a general tool for analyzing time series data. So if you're interested, you can just check out this repo. There's actually also one paper that was written by people in the group for a parameter estimation for kilonova light curves, which is using this Amplify setup. And I personally are also in contact with people doing like some experiments in the Laboratory of Nuclear Science at MIT who are also interested in this like frequency denoising part. So yeah, if you're interested, I'm happy to chat, and feel free to also check out the code. Yes, thanks.
Thank you for very nice talk. Any more questions from here?
I have a question.
Oh, yeah, there are questions. So we have question here first, Axel.
Oh, go ahead.
Yes, concerning the last part of the parameter estimation, so how to generate this problem? So is there like a single unique solution for each event on the best?
Yeah, I mean, what do you mean by how general it is? So
Degenerate. So
it
like,
degenerates.
so if you have a given signal, my question is like, is there like a unique set of parameters that creates exactly this signal? Because typically when this also come like in astronomy that you have things like, I don't know, that you have like an inverse problem somehow, right?
Okay, so you're meaning like
some uncertainty involved, and then like the reconstruction is not unique.
Yeah, so you're meaning basically, let's say I have like a set of masses or so, this gives me this series, but the series could also be like from another like, okay.
Exactly, it could be a different combination of
covariant program.
Exactly, that creates like the same, basically the same signal.
So I'm not sure how much this was actually. The thing is, here Amplify at the current setup is basically trained on binary black hole mergers specifically. So, and I believe there it's relatively straightforward. So, I mean, this is also like how we do the mesh filtering things at the moment.
There aren't degeneracies in this kind of
Yeah.
So you only have two sources, right? So in principle, you have a line.
Yeah.
Right?
Yeah.
Now, if you inject the lineage prior, right, you can constrain things, but you often see that you have nodes, right?
But
there was an example.
Yeah, I think like here, but the thing is also that this degeneracy, I think it's mostly coming from the fact that in this plots, Virgo is not like running or like not included. I think it was perhaps running. I think.
Yeah, if you can see the signal in Virgo,
Yeah.
Yeah.
So this is like not a real degeneracy in the terms of like really the parameters, but more like that we just at the moment measure. What I also know about is like polarization can sometimes be an issue because it's mostly determined by like how detectors are actually positioned. And then certain polarizations can be like basically that we like miss them in one detector or something.
Yeah.
So this is also, but like polarization here is actually also a parameter that is very hard to determine. So like, and here Amplify is mostly like, I mean, is the localization part and also the mass that we're mostly interested in by now.
Yeah, I was wondering if you know how this different compares to like how fast
This is a good thing. So I do not know how it compares actually to this. I know that RigRig is a very like general way of doing this contrastive things. I personally work at the moment with Sinclair, also in the particle physics application. I think in general, in more like practical terms, RigRig is relatively hard to train and to make it converge. No, you Phil disagreeing.
I mean, absolutely fine. They're both, I would say they're both equally good. There's no obvious.
Okay, perhaps like, okay, I like reading a literature, I feel like usually people say Sinclair is easier to train, but like, I mean, I haven't like, beside this, okay. Yeah.
So what is this? Sorry, what is this other?
So Sinclair is basically having like a temperature parameter where you form like positive pair. So basically here we have this like loss that is structured like this. And then in Sinclair, you have basically you define what is a positive pair by like just also another version of you. And then you divide basically by all of your negative pairs. Let's say you have a picture and then you just like mirror it. And then this is your positive pair and all of the other pictures would basically be in the negative pairs. And then you have a temperature parameter that tells you in this Latin space how far away you want to push the classes or how much you want to cluster them. And then there are, of course, also versions of like Sinclair as like being supervised and all of these kind of like tricks that you can do for that. Yeah.
Okay, we have Jeff online. Jeff, please talk.
Yes, thanks. I'd like to focus a little bit on, I guess, what you might call the pre-processing that you discussed. In all of the areas that you mentioned, let's say tapering, denoising, filtering, and even selecting what witness channels to use and so on, there are lots of choices. There are millions of tapers and the neat idea of multi-tapering. And you find in the literature, all of these are applied by various people and in various analyses and so on. What I would have thought was that machine learning might allow you to sort of incorporate all of these and let the so-called, I like to think of the concept of automated intelligence rather than artificial intelligence. But anyway, automate, considering a lot of options. And unless I missed the point, your scheme doesn't do that. It sort of fixes on, you fix on a particular denoising scheme, or in some sense, do you effectively consider a whole range of denoising schemes?
So in this sense, what we do here as a pre-processing, it's basically whitening and bandpassing the data. So in this sense, like when you consider whitening, like a kind of like, I don't know, like a form of denoising, yeah, then for sure, yes. And then additionally, we normalize the time series data before we pass it to the neural networks. So in this sense, yeah, we do some pre-processing by hand. We're actually currently also checking out things where we directly just take the time series because they're like some progress in literature of like other models that might directly learn something like a Fourier transfer projection as well. But yeah, I mean, the ultimate goal is always like, I mean, to do more things automated. So like letting the algorithms figure out more and more. But then, of course, it comes also usually with the cost of making like the networks bigger. And especially now when we speak about low latency and things, it's always like, of course, a trade-off, like how actually like big we want to make the networks and also how complex. And at least from my personal point of view, I think like these things of pre-processing that we apply here are kind of like very standard in the way of gravitational wave physics. So it's like something that we usually do before we anyway look at this data. So I think it's not something, I mean, we can get rid of this at some point, I believe as well, but I do not think that this is kind of like very much the need at this moment.
Yeah, sure. And you're right. There are standard methods and choices for parameters even for all of these things, but they do make a difference. Everything you show here,
yeah,
it can be different and better with different schemes. Even the whitening, the dividing by that square root. You know, there are other ways of doing that might improve things. And it seems to me a great promise of artificial or automated schemes is to compare those effectively by, you know, putting them into some neural network and allowing all possibilities or something like that. Anyway, sorry to ramble on, but that's just a thought about how this general approach might be further generalized. But anyway, thanks for this nice talk.
Thank you.
Any more comments? Oh,
Do you have any idea how much of the approximation error of normalizing flows impacts the results, or is it really kind of not that much?
So this is a good question. I don't know actually by heart, no, I just don't know. Like, I do not have a number for you by now.
Which normalizing flows are you using?
So this is an autoregressive flow.
Maybe just related to this, I mean, you've shown the comparison also like of the confidence regions against the other algorithm, and they're different, right?
Yeah.
And the question is like, how well is it understood?
So this is a bit hard to say because these are real events. So we actually don't know like what the real parameter is. So I believe that this like degeneracy that you can see, for example, in base that, I mean, you see that this is not clear anymore in the amplify. I know that people have looked into this a bit, and this might be that like perhaps something is not sampled well, but like here it's really hard to tell because we do not know if this is correct or this because of the real event. So I believe in general we can kind of like trust this very well because we know like I mean this is like 500 binary black momentures where we actually know the parameters, and this is showing that we do not bias anything or so. But I think also in terms of this like real life examples, like this is just like starting now basically to like understand this a bit like better, and yeah. I think like as I also said during the talk, I think one thing that was kind of or that could relate is that in principle these algorithms as trained at the moment pick up better louder events, which is just because they're like easier to get information from. So we see that usually in amplify that the louder the event is, the smaller the 90% area in localization gets versus the other algorithms. And this is just something that we also see in A-frame, for example. The louder the event is, the better we can outperform basically everything else. And we are also currently like working on this, particularly looking, for example, in this training strategy, if there's like a better training strategy to make it basically better pick up this like these events that are in general like smaller. But then the problem is also that in all of these applications at the moment we fix the kernel size. So we, for example, for A-frame we have 1.5 seconds, and then the less loud an event is, the longer it persists over time. So we actually look at only one part of the signal, rather for the louder events we really look at the whole signal. So this is also something where we look in different architectures or so, because we would like to basically make the machine learning work better if we have like varying signal length. This is also one very big thing when we talk about binary neutron star mergers, which like, of course, in terms of multi-messenger astronomy, very interesting because they have this electromagnetic counterpart, but they are usually very long. They have very long signals, and this is not as easy to pick up because we would either use like very long kernel length, but then you pick up a lot of these like longer duration noise. So it's like always a bit of like, I mean, these are like this kind of challenges that we face at the moment that we're currently at the moment.
So, for the localization, can you use different data, not the gravitational wave data, but some other variable sources data to improve the localization? Which it's just your algorithm. So thinking about some variability in binary systems. So use something which we know and you know where it is, and so see if you can improve your localization. I don't know.
This is actually a good point. Yeah, I don't know how, because I guess you're speaking about a system that is like somewhere very well understood and measured how far it's away. And then we have, so I don't know from these systems, like, because then we would need a gravitational wave, like signal coming from
okay, so
like, I mean, this is something, we can for sure do. I think like this is also a bit like this work towards this direction, that we have this parameter estimation for kilonova like curves, like for sure, like
because you know where it is on the sky.
So
waves are huge, the big space. Any more comments? All right, thank you very much.
Thank you.
Thank you very much.
All right, I just want to comment that next week we got Justina talking about pileup.
Oh, right, yeah.
Okay, the next week?
Yeah.
Great, thank you.
Okay.
Now let's know what food do you want? We still have some food here, right?
Yeah, sometimes these are all.